All right, moving on to the iterative prediction method. And we're going to be looking at a situation with constant net force, which is, of course, the easiest of the circumstances. All right, so according to the momentum principle, if the change in momentum is not zero, then this would imply that there is a net force that is non-zero acting on the system. The simplest case is a constant force. So that means that the change in force is equal to zero, or the change of the magnitude of the force is equal to zero, and the change of the direction of the force is equal to zero. So this isn't the most realistic as far as real-world situations, but it's very useful for modeling and illustrating the concepts which then can be applied to more complex systems. So a common constant force is the force of gravity on Earth. So in this case, force would be equal to mg. So a 1 kg object is attracted to Earth with a gravitational force of 9.8 newtons. And 2 kg is attracted with a gravitational force of 2 times 9.8 newtons, and so on and so forth. So we'll get into proving where this comes from in chapter 3. For now, just know that g Earth is 9.8 meters per second squared, or newtons per kilogram. So the final momentum will be equal to the momentum of the now plus the F net times the length of time that the force has been applied. And this will take all the interactions into account. So let's take a look at what we mean by taking all the interactions into account. Because it turns out that the momentum carries with it the history of where it's come from. So for example, let's say we have a hockey puck and it's being struck with a stick. So in the very moment of impact, the initial momentum is going to be 0, and we're looking at time naught, or t naught. Then the puck is going to start to take off, and the force from the stick is going to start to decrease. And this happens at t naught plus delta t, and then we would see that the momentum would really start to take off as the stick is starting to lose contact with the puck. So this is t naught plus 2 delta t, and then finally the puck now just has momentum and F stick is 0. And so what we see is that this puck in each step is carrying with it the history of what's come before it. So you can analyze a path of motion at any given time. So all the past interactions give you this. And this is very useful because it basically means you can choose the easiest part of the path to analyze, and you'll get what you need. Okay, so all of this sets up the premise behind the iterative method, where we'll be calculating this step by step by step and mathematically. Okay. So, the iterative prediction of motion. So this allows you to predict future motion. And you do so by chunking up the total path that something travels and calculating it in little tiny manageable chunks. So in order for this to work, you must choose a time chunk small enough to assume delta F is approximately 0 and delta V is approximately 0 so that we can make some useful estimations. So the iterative prediction of motion Step 1, you calculate the net force. Step 2, you update the momentum. So P future is equal to P now plus F net delta T. And then step 3, you update position. So R future is equal to R now plus V average delta T. And for this, to go after V average is going to be approximately future momentum divided by mass. And we'll explain why that's true later on, or why that is a good enough approximation later on. And what you could do is you could, if you just repeat these steps, you could predict an object's entire path of motion. Now, you'd want to use a computer program for that, so we only do a couple steps just to illustrate how this works. So, for example, if you have a ball moving without air resistance or negligible air resistance, you have a constant force situations. By the way, at low speeds, it's actually very reasonable to neglect air resistance. We'll see in a later chapter that air resistance is dependent upon velocity. So the plan of action for analyzing the path of this ball, you'll need 2 initial values, either given to you or the materials given so that you can calculate them. Initial position and initial momentum. Then we will do repeatedly you want to find F net now, then apply momentum principle to find P future, and then use P future divided by M to approximate V average, and then use V average to get the position after some given delta T. Okay, so let's practice using the iterative method on a very simple situation. So we're going to consider a golf ball with mass being equal to 46 grams hit with velocity initial of 65, 45, 0 meters per second. And this is after loss of contact with club. Okay, so to do the iterative method, we're going to need the initial momentum. So this is going to be equal to 0.046 kilograms times 65, 45, 0 meters per second. Initial momentum is equal to 2.99, 2.070 kilogram meters per second. And our initial position, which is given, is 300 meters. And we're going to use delta t, which is given, of 0.5 seconds. Okay, so now we have everything we need to begin iterating through this problem. So step one, we want our net force. So in this case, we're just going to have the force from the Earth, and it's in negative y. So F net now is equal to mg is equal to 0 minus 0.046 kilograms times 9.8 newtons per kilogram, 0. F net now is equal to 0 minus 0.4510 newtons. Okay, so that ends step 1. 2, future momentum. So P future is equal to P initial plus F net now delta T. P future is equal to 2.99, 2.070 kilogram meters per second plus 0 minus 0.4510 newtons times 0.5 seconds. P final is equal to 2.99, 1.840 kilogram meters per second. So next up, for step 3, our future is what we're after. So our future is equal to R now plus V average delta T. And remember, V average, we're going to use the approximation that it's approximately the final momentum divided by mass. So this is 2.99, 1.840 kilogram meters per second divided by 0.046 kilograms. V average is approximately 65, 45, 0 meters per second. And so we can use that to calculate future momentum, which is 300 meters plus 65, 40, 0 meters per second times 0.5 seconds. Our future is equal to 35.520 meters. So if we observe what happens, so force is only in y, so there is only a delta P in y and only a delta V in y because force is in y. X stayed the same the entire time. So why exactly are we using P future to go after V average instead of the average of P future and P now? The quick and dirty answer is that as long as delta T is small, P future divided by M is an adequate approximation. And the arithmetic average is not always an appropriate approximation, and we'll talk in what circumstances you can use it and in what circumstances it's insufficient. So arithmetic average is sometimes more accurate, but not always. All right, so we have just calculated one iteration of motion of this golf ball. So how would we start step 2? Well, for step 2, P future becomes P now. So P now is now equal to 2.99, 1.840 kilogram meters per second. And R future is R now. And so R now is equal to 35.520 meters. So now we can go ahead and do the next step. F net does not change. It's still equal to 0 minus 0.451, 0 newtons. P future is equal to 2.99, 1.840 kilogram meters per second plus 0 minus 0.451, 0 newtons, 0.5 seconds, which is equal to 2.99, 1.610 kilogram meters per second. So this is 1, 2, and then 3, we want to calculate R future. So R future is equal to 35.520 meters plus, and now we're going to embed the V average calculation in the expression. It doesn't matter what you do. Do what keeps you most accurate. They're the same. It's just and so we get that the future position is equal to 68, 37, 37.5, and 0 meters. And we could just keep repeating over and over and over and over again. We're not going to, because it starts to get a little bit ridiculous. But essentially you would just see that the path of the ball, you'd have the F net going down, future momentum of the now, future momentum connected by F net, and so on and so forth. It would look like that. All right, so this wraps up section 2.4.